Today we're going to be looking at the physics of tyres. Now in particular we're looking here at the physics of performance tyres. How do we make them perform better and how do they work? So I'm not going to go into some of the really basic stuff. If you really want me to go into the real basics on like what is a tyre, ask for a video. But I'm going to go through how they work in a physics sense. Rolling on from that point, I'm not actually going to go into here on how we use the information that I present today. Things like designing Ackerman, designing suspension geometry. I'm not going to go into that. It's just going to end up in too long a video and will just be unmanageable. So again, if you want that, request that. Let's begin. The tyre is one of the simplest looking parts on the car. It just looks like a basic rubber block when you look from the outside. But it's really one of the most complicated and it is the most important thing on the car. Think about it. All your loads, everything to do with your acceleration, all goes through the tyres. So we have to manage the tyres. The whole car is about managing the tyres in the best possible way to get the best possible performance. In this video, I'm only going to scratch the surface of what's involved in tyre physics. And maybe you can do a bit of research on your own, but hopefully this will give you a good fundamental base. Before we get to the tyre, we need to talk about friction. Now, a lot of people taught friction, particularly in engineering degrees, as a sort of constant thing. You have a static friction and a dynamic friction. Now, the static friction will basically hold your force up to a point, and then once you exceed it, it will switch over to dynamic friction. Now, we can kind of see that in this graph. If we have a force that we're applying here, and this is the frictional force, as we apply a force, the friction force will rise to match. But eventually we'll reach this point where we exceed the coefficient of static friction. Then the frictional force will drop down to a certain point and continue. This can be seen in the equation Fr equals mu n. This being the normal force on an object, and this being the frictional force, where this is the coefficient of friction. Now when it comes to tyres and things like that, this doesn't really apply. The problem is that we have deflections in our tyre, and that changes the ball game. If we were to consider that as we apply a force, let's say the tyre tread is static, but the tyre wall is deflecting, we can see that if this was our force that we're applying, so this is our distance and this is our frictional coefficient, we can see that it would hold constant as the tyre is deflecting over, and then it will start to slip, it'll start to slide. So you'll drop down onto the dynamic coefficient and go along there. But in reality, the deflection is happening the whole time. So we're really seeing more of this action. But of course, being a real world system, nothing ever works out so that it's an instant step. Everything happens smoothly. And we've got rubber that's flexing all over the place. So when these curves smooth out a bit, we end up with something more like that. And this is kind of starting to get to the shape of what a real world tyre friction curve looks like. Let's get into those. If we look at a tyre on a car, let's say that this is a cross section through a wheel. So this is the actual wheel itself, this is the tyre here. If we consider this first case here, this is just the car sitting on the ground. The tyre is sitting at a relatively normal point and it's just going to be going along. If we turn and apply a lateral force on the bottom of the tyre here, it's going to pull the bottom of the tyre across, giving us this. Now, as the tyre is rolling along, you're pulling over each bit of the tyre again and again and again. It keeps going. So the result of this is that as the tyre is deflecting through a corner, this tread at the bottom is going to actually see a differential angle to your wheel. So you'll turn into a corner, and let's say you turn your wheel 5 degrees. The tyre may only be turning effectively on the ground 3 degrees. And this is the concept of a slip angle, and it's a good measure of how your deflection in your tyre is related to everything. Let's have a look at what we can do with it. For suspension designers, it's usually best to explain your lateral grip as a function of your slip angle, because that will be roughly constant for any given tyre in a given normal load situation. So we can see from that graph that I was showing you before that we were relating our force to our deflection, and what shape did the curve get? That. Now, because our alpha is roughly related to our deflection, we can imagine that this is the curve for a tyre. Now this bit here we can see is the point of peak grip, which corresponds to a peak slip angle. And this is what suspension design is all about. You want to optimize your slip angles for peak grip. Obviously driver skill and ability comes into factor on it, but this is what we aim for. Another thing that's interesting to see here is that For the same level of grip that's below peak grip, there are actually two cornering conditions in which you can end up in the same area. Both are two very different slip angles, particularly if you were to get lower down the line like this. This is why things like drifting can still work and get around corners. Now, the important thing to note here is that we're looking at a deflection and a force here. So we can think of the area under the curve as energy being put into the tyre. So if you drive on this side of the curve, you're going to put less energy into the tyre. If you drive over here, you're going to put more energy into the tyre. Now, what does this equate to? Tyre temperatures. If you're driving on this side, you're going to be getting those tyres hotter. You're probably going to overheat them if your car's not set up for that. If you drive here, you'll keep them cooler. Notice both have the same lateral grip, even though this will result in a dramatically higher slip angle. Of course, in addition to slip angle, there's such a thing as slip ratio, which is in the longitudinal direction. So if you think of a drag car, when it's getting off the line, its tyre sidewall will deflect longitudinally, and that will give it a slip ratio where the center of the wheel will spin faster than the outside of the wheel. It will actually have a faster rotational speed. And what that basically equates to is that we can now think of our total grip in both slip ratio and slip angle. Now, when we factor that together, we can get something known as a friction ellipse. The friction ellipse basically details your longitudinal acceleration versus your lateral acceleration, so that at any given point, you can know what your peak grip is as per your tyre curves. So let's say I want to come into a corner with a little bit of lateral acceleration and a bit of braking, then I'd perhaps be looking at this point here. Or maybe if I'm accelerating, look at this point here. Depending on convention, it could be the opposite way around, but you get the idea. Now, these friction ellipses can come in many different shapes. They can be like that sort of thing, or they can be very circular. Now, depending on this, it changes how you want to drive the car. A friction ellipse with very pointy corners like this, I believe the old Michelin F1 tyres used to run this. Back when they were Michelin and Bridgestone, the main difference is that one of them had a very round frictional ellipse. One of them actually had a fairly square one. And it meant that you can drive this car faster by actually braking into corners or accelerating out of corners. Whereas one with a circular ellipse, you kind of want to be sort of doing one or the other. You don't want to combine. And usually a circular ellipse will have higher peak values, but it just means that the combined value is low. So it changes how you drive the car. One is not necessarily better than the other, they're just different. That's the intro to basic tyre curves and basic tyre physics covered. I'm now going to split off into two sections, road and off-road. Let's start with road. There's a few tutorials and instructionals I've seen on YouTube that talk about tyre load sensitivity. I believe Engineering explained at least one quite recently. And while they only scratch the surface of what we're dealing with here, they deal with the basics of the filling of the rubber into the road surface. And on a microscopic level, the rubber will basically be trying to get into microscopic grooves on the road. Now, it will try and conform like that. As you increase the load, it will just deflect more and more into that. And that's why the friction coefficient is usually treated as constant regardless of your normal load. The problem here is that eventually the rubber will start to fill it up too much, and adding more load won't necessarily give you that much more grip. And that's the basics of like tyre load sensitivity on a microscopic level. Of course, like I said, this is only scratching the surface. There's so much more to do with normal loading. Let's get into some of it. Before, we were talking about slip angles and tyre curves. As I said, the slip angle is related to your stiffness of your tyre. So it's conceivable that two different tyre constructions will produce different slip angle curves even for the same rubber compound. Think about that. If we have one tyre curve like that, let's say we now get the same compound but soften our sidewall. It really is quite spongy now and it will smoothen it off. We end up with a curve like that. It will end up with the same total grip at the end, same peak grip here, but we've now shifted the curve massively. So this may be originally at say 3 degrees, and this is over at 7. This is a more predictable tyre immediately. We can see that because the curve is longer, it gives you a bigger margin for error. Here to here is much larger distance from here to here. You don't have to be as on point and as precise. So if you're a less experienced driver, or say in a road car, which is really where we see these larger slip angle tires used, you'll find that this is the correct sort of tire. Whereas more twitchy cars, faster cars, real race cars with professional drivers such as Formula 1 cars will be using these smaller slip angle tires. You may ask why we don't just all go for these larger slip angle tires if we can get the grip the same. And it comes back to that energy loss thing I was talking about. We'll get more heat in the tires if the slip angles are larger. But that heat has to come from somewhere. Now, where does it come from? It comes from drag on the tires, not aerodynamic drag, but rather drag on the ground. So if you are running this higher slip angle, you're going to see additional backwards force on your car and you're going to lose power. That's why these narrower tires are better. In addition to that, you will also have superior response on a tire with less slip angle. If anyone's driven a car with stiffer sidewall tires, you'll know what I mean. They feel very sharp on point. And that's the trade-off. You'll have a car that's more efficient and more responsive, but it's harder to drive. And really, everyone kind of knows this, but this is the reason why. An interesting point to note here is that when I first reviewed the GT86, I talked about its tires having too soft a sidewall. And the interesting thing here is that it's also a car that everyone says has excellent handling feel, it has excellent steering feel, and I completely agree. But what have we got here? We've got more energy going through the tires, we've got bigger areas. Softer sidewall equals better feel. And that's one of the reasons why that's the case. Sorry to switch to black pen here, but it appears my blue pen has died. Consider that if we can get different sidewall constructions to achieve different flex patterns and therefore different tire curves, what happens if we get the same tire and then increase the normal load? Will it cause just a linear deflection? No, because the construction will vary. When you apply more force, it will change how the tire deflects. And this is actually one of the key things when it comes to suspension tuning, is that your peak slip angle will change depending on your normal load. Let's have a look at that. Let us consider one tire curve here. We go the same tire, we then put less normal force on it coming down from the top. It will have a curve like that for this particular tire, okay? This is just a generic case, not specific. If we then have a higher normal load, the curve may look like that. Let's identify our points of peak grip here. We have a point here, a point here, and a point here. If we were to connect those dots, we end up with the curve like this. This produces another curve that we can use to our benefit as suspension designers, which is peak lateral force slip angle, so the slip angle at which we achieve our peak lateral force and maximum grip, versus our normal load. Converting our previous graph into this graph, we can see that if we pick at our low load case, we take a point, the alpha is lower, so here. At our medium case, alpha is higher. High load, higher again. So this gives us an idea of how we can tune our tire slip angles when we have weight transfer across an axle. Now, of course, if the car is cornering, you're going to end up with a weight transfer due to the center of gravity being higher than the ground. This means that you will have to change your slip angles on your tires left and right depending on how hard you're cornering. This is one of the reasons why Ackerman is different to what you normally think. Now, I'm thinking of doing a video on Ackerman. If you want that, let me know. Of course, not only is the peak slip angle changing for the different normal loads, but also the peak grip. The coefficient of friction is not constant, like I was talking about with that load sensitivity. And this is one of the reasons why people run wider tires. If you have a wider tire, it's easier to get the same contact patch length for a given contact patch area. Now let's have a look at the contact patch, because that's an important thing. If we look at a tire from above, it will obviously be pressed against the surface somewhat. This will cause a contact patch kinda-ish like that to form. Not quite, but you'll get the idea. This contact patch will change shape depending on the loads. We could see before there's tire deflections. And depending on the slip angle, the contact patch area changes. Now this is realistically what's causing our load to drop off and rise nicely. And it's because as this contact patch deflects to the side, it can get weird shapes, kind of like that and things like that. And this shaping will vary the area. This goes back to the tire load sensitivity part, where changing the area of the contact patch will vary your total friction coefficient. Obviously, running a wider tire will help you increase your contact patch area if you drop your pressures appropriately. You have to remember that your tire pressure is really a function, this contact patch area, is really a function of your tire pressure. That's why Formula SAE teams can be seen running tire pressures of 10 psi sort of thing, whereas on a road car you're at 40 psi. I believe Formula 1 teams are 13 to 15 psi as well. So keep in mind, wider tires, you have to get your pressures appropriate. Of course, this is where I bring up the tapering of grip compared to normal force. As the normal force increases, the grip force will go up. Then as it gets to the top, it tapers off. Now, what you can see here is that if you actually design a car that's over-tired, so you've got too much rubber, this bit here is roughly linear. So if we look at our weight transfer, as the car shifts side to side, we may increase our load on one side, but it won't relatively strip grip off that axle. The axle will maintain the same grip it had before. You may think, oh great, we've got the same grip, this is perfect. But the problem is that how do you set up a car that doesn't have a change in grip when there's roll? An anti-roll bar will have zero effect. It's very hard to tune a car like this. So you want to size your tires so they're appropriate, but you still want it to sit up so there's a slight change, or it's really, really hard to tune. And let's not even begin to mention tire temps, because people who over-tire cars with slicks and things like that, like autocross cars, will never get them up to temperature in a brief lap as that. And that's why you see autocross tires running insanely soft compounds. SAE car tires, the rubber you can basically stick your finger right through. Again, wider rubber is not without its complications either. If we consider a tire with camber, now of course camber is executed so that when you get that sidewall deflection, the sidewall comes down to flat. So it sits up like this when it's going down the road, you deflect it and you get a thrust, because essentially your tire is sitting, obviously exaggerated, like this against the road. As this deflects, this will pull this around to this profile, which is ideal. Now with a wider tire, it's sometimes harder to get this to work. With correct camber setup, it's not an issue, but if you don't know what you're doing, wider tires are going to make your life even worse for you. Just as a final note here, I'd like to talk about this shape of this contact patch here, because we can see it's been deflected, it's no longer on center. The centroid of the contact patch is over here. Now, this is essentially a trail in the rubber, it's known as. And this misalignment means that when you have your tire force there, or going a bit that way, you get a torque around the center axis. Now, of course, things like caster can move where the axis of rotation of the tire is, but you can see that this torque will still occur regardless. And this is what gives you a lot of your self-aligning torque in corners, is the deflection of this contact patch. And this torque is also not insignificant in handling either. It will change the yaw behavior of the car. So you've got steering feel and yaw behavior. And this is why I was talking about the tires having more feel when they've got more deflection, more slip angle, because this will move more. You'll end up with more feel because this distance is larger. On the less slip angle tires, where this area moves less, you'll find that this point might only be here. So you end up with a shorter moment arm and less overall torque on the tire, and that's why your tire gets less feel. When your car starts understeering, of course, this contact patch will shift so that this will move back up towards, and that's why you feel the steering loosening off. But a thing that you should probably know here, which is something that most people don't know, is that the point of peak self-aligning torque is actually very much below the point of peak lateral grip. If we plot the self-alignment torque and the peak lateral force on the same graph, we see a very interesting thing. As you know to death by now, that is the lateral force for a tire. But due to the contact patch deflection, the peak torque will actually go more like that sort of thing. And what's very interesting to note here is that this is the peak torque through your tire from the contact patch. This here is the peak lateral force. Obviously, because the contact patch is deflected backwards, that lateral force is an important component in your steering feel. But we can see that because the contact patch will deflect forward a bit, even though the caster is giving you a moment from the lateral force, it's reducing faster than the lateral force is increasing. This means that technically speaking, you have to drive your tires beyond the point where you as a driver may feel through the steering wheel that it's understeering, because it's not actually understeering. And this is why the overdriving technique you see by many famous drivers, where they sort of get it and they go like that works so well, because they are naturally driving beyond this point here, and they're sort of alternating between there and there and there and there, instead of most people who would be just driving it here. So you can see the average grip that they're experiencing is actually higher. And that's the key behind successful driving on many road tires. F1 guys are usually very good at determining from the lateral forces they're doing it right. To cap off the road section, there's obviously a lot of factors to deal with the tires that I haven't mentioned here. You've got kingpin inclination angle, caster, camber, proper detailed description on Ackerman, slip angle of the chassis, all these things. And these are all things that I can go into detail in videos for, but I'm pretty sure this video is already blowing well out of proportion, so if you want it, just mention. Now we get to the off-road tires. This is something that I don't see much discussed on the internet, and it's not even that well documented in books, and I feel a lot of this is because people don't understand off-road tires well, and that's including myself. I'm going to put it out right now, I am no expert on off-road tires, but I do know a lot about regular tires, and I do know a fair bit about off-road, so let's see how we go here. To start with, on asphalt or road racing, you work the tire. You're all about working the tire, the ground is pretty solid. On dirt though, it's not as simple. You're working the ground and the tire. It's a harmony between the two of them. And because dirt surfaces and rocky surfaces, any sort of loose surface can actually slide, what you end up with is an effective slip angle not only on your tire, but on your road surface as well. And this is what makes off-road tire analysis so difficult, because depending on your surface, your tire curves can be completely wrong. Like, you can end up with really weird grip angles. As you could probably tell from my road section, road tires don't need tread because they fill the asphalt. They only need it to displace water in the rain. Off-road tires, on the other hand, do need tread because they need to dig into that ground. And if you were to consider the ground here, we come along with a flat tire, just dead straight. Now, unless we're dealing with something like sand, which is just going to deflect really easily immediately, we need to have some way of cutting up this ground. If we just have a flat tire, it's just going to skim. It's not going to give us great grip. So we end up putting lots of grooves in our tires. Now, obviously, the location, nature, number, all that sort of thing in our grooves depends on whether we're running in mud, rocks, sand. It all makes a massive difference. But let's just go with the basics now. We have these grooves, and they will cut into our material. So what we'll end up with is that this will sort of bulge out to meet there as this presses down on it. So our new ground plane will go sort of up, up, up. And obviously the lateral grooves across, they will help with the forward grip by cutting that way. The key thing to notice here is that we're actually cutting, and that means that you need tires with lugs with really sharp edges. I was at an off-road race round one time, and the guys there, really big expensive guys that like you can't hope to match on budget, they have tires, like $1,000 a pop tires, that they were changing out after each round of the race, and that was like a 4-round race weekend. And the reason they do that, the reason why off-road is changing those tires so much, even though they're not really getting that worn because they're quite hard tires, is because they want to maintain these razor-sharp edges. And the sharper you get those edges, like if you take a close look at a rally car tire, those sharp edges will bite nicely into the ground and really help with that. The aggressiveness of the tread depends too on what you're doing, like I mentioned previously. Dirt bikes, which are quite light but often drive in really loamy peat, when you're talking about like a motocross or something like that, obviously have those little knobbies, and they work great when you can really dig in hard. But if you were to get that and ride it on a really hard loose dirt, like I've often ridden my bike against people on full knobbies on that, you'll find that it actually won't have, if it's really hard pack, that much more grip than, say, a more sort of road bias tyre, which has bigger treads and a larger sort of surface area with less cutting area. Obviously, another factor for off-road racing is your contact patch size. Now, everyone knows that contact patch size is the thing, but as we can see here, we're looking at cutting and not necessarily filling. So the contact patch size may not always work how you expect. Sometimes you want a really skinny shaped contact patch. So it's all about optimizing not so much your overall size of your contact patch, but your shape. When we look at our tire, we can see from the side that it deflects in this way, right? It's getting squared off at the bottom. Many people think the only way to increase contact patch is by widening the tires, and that's why you see so many of these big off-road four-wheel drives with these massively wide tires. And I never really subscribed to the hugely wide tires for off-road vehicles thing. My family's Troopy has like the skinniest tires in existence, and I've never driven anything with more grip in low speed. And a lot of this is due to the fact that with a larger diameter tire, you can create a big contact patch, an equivalent contact patch to a wider tire at a smaller diameter. This is all about making the contact patch long instead of wide. So we have two tires. This one here, small diameter and wide. This one here, large diameter and narrow. We'll end up with a contact patch that resembles that on this guy, and a contact patch that resembles that on this guy. Now, if we assume that these are the same area, we can have a look at this angle here. See how much shallower this angle is because we're at a larger radius and how much steeper this one is? This will help greatly with your rolling resistance, and it's one of the reasons why when you see cars in desert racing and big trophy trucks and stuff like that, they run those massive like 37-inch, 39-inch tires, and they can get this nicer angle. Whereas the small guys sometimes struggle in the looser sand. But of course, it's not just sand that this applies in, there's many surfaces. And look at these two shapes, okay? If we're running through a soft surface, like a loamy peat or a soft mud or something like that, this kind of looks a bit like a sort of rudder or a daggerboard on a boat. And this looks kind of, you don't even know what it's doing because it's so wide. It's not going to cut nicely. It's not going to give you that directional stability. And this is why often cars with these really skinny tires work so well off-road. Even rally tires are often really a lot skinnier than you'd expect on rally cars. And that's for this reason. Finally, for off-road, I'd just like to talk about the slip angle consequences of driving off-road and the tire selection for off-road and how that changes your slip angles. Obviously, compared to most road tires, or low-profile tires anyway, we end up with a much higher sidewall on an off-road tire for our given width. What this means is that for a given force down here, we'll end up with a larger deflection. Now, this means a larger peak slip angle. But obviously, we have a smaller lateral grip off-road because we're slipping more. So this sort of balances out, and depending on the construction, it will be roughly the same. But there's another factor here, which is that off-road tires are often designed to absorb a little bit more bump. So again, they soften the sidewalls a bit. That's why we end up with more slip angle overall. Factor in that additional slip angle, effective slip angle coming off the ground, and this is why you see off-road cars running at much larger angles. If you think about it, the rear tires can't steer. So you've got to get your slip angle from the rears by basically oversteering into a corner. And this is why oversteer is so desirable on off-road cars compared to on-road cars where it's generally not wanted. Because you want your off-road car to oversteer because you need that bigger slip angle at the rear. So you may have a peak grip slip angle of say 20 degrees. So that means your chassis slip angle has to be 20 degrees to get that out of there. And many people ask me why you use oversteer off-road, and that's largely the reason. But like I say with all of this, I'm not an expert in off-road tires or anything like that. On-road is my speciality. That's the entire reason I'm building an off-road buggy, so I can learn more about it. So take everything I say with a grain of salt. I hope that explains a lot of things for people. Thanks for watching. Probably said it 500 times in the video, but if you do want any of these features I mentioned in different videos, feel free to leave a comment. And hopefully I'll see you next time.